Philippe Guingambra (1764–1838), a student of Lavoisier, first obtained phosphine in 1783 by heating white phosphorus in an aqueous solution of potassium carbonate, perhaps because of its strong association with elemental phosphorus. Phosphine was once regarded as a gaseous form of the element, but Lavoisier 1789 recognized it as a combination of phosphorus with hydrogen and described it as phosphore dihydrogene, phosphide of hydrogen. In 1844, Paul Thenard, son of the French chemist Louis-Jacques Thenard, used a cold trap to separate diphosphine from phosphine that had been generated from calcium phosphide, thereby demonstrating that P2H4 is responsible for spontaneous flammability associated with pH3, and also for the characteristic orange-brown color that can form on surfaces, which is a polymerization product. He considered diphosphine's formula to be pH2, and thus an intermediate between elemental phosphorus, the higher polymers, and phosphine. Calcium phosphide, nominally calcium phosphide, produces more P2H4 than other phosphides because of the preponderance of pp bonds in the starting material. The name, phosphine, was first used for an organophosphorus compounds in 1857, being analogous to organic amines, NR3. The gas pH3 was named phosphine by 1865, or earlier. pH3 is a trigonal pyramidal molecule with C3V molecular symmetry. The length of the pH bond is 1.42 A, the H-pH bond angles are 93.5 degrees. The dipole moment is 0.58 d, which increases with substitution of methyl groups in the series, CH3PH2, 1.10 d, CH3 2pH, 1.23 d, CH3 3p, 1.19 d. In contrast, the dipole moments of amines decrease with substitution, starting with ammonia, which has a dipole moment of 1.47 d. The low dipole moment and almost orthogonal bond angles lead to the conclusion that in pH3 the pH bonds are almost entirely p sigma p, s sigma h, and phosphorus 3's orbital contributes little to the bonding between phosphorus and hydrogen in this molecule. For this reason, the lone pair on phosphorus may be regarded as predominantly formed by the 3's orbital of phosphorus. The upfield chemical shift of the phosphorus atom in the 31p NMR spectrum accords with the conclusion that the lone pair electrons occupy the 3's orbital. Fluck, 1973. This electronic structure leads to a lack of nucleophilicity in general and lack of basicity in particular, pKa equals -14, as well as an ability to form only weak hydrogen bonds. The aqueous solubility of pH3 is slight, 0.22 ml of gas dissolve in 1 ml of water. Phosphine dissolves more readily in nonpolar solvents than in water because of the nonpolar pH bonds. It is technically amphoteric in water, but acid and base activity is poor. Proton exchange proceeds via phosphonium, pH4+, ion in acidic solutions and via pH2- at high pH, with equilibrium constants Kb equals 4 × 10⁻28 and Ka equals 41.6 × 10⁻29. Phosphine burns producing a dense white cloud of phosphoric acid, pH3 plus 2O2 right pointing arrow H3PO4. Phosphine may be prepared in a variety of ways. Industrially it can be made by the reaction of white phosphorus with sodium or potassium hydroxide, producing potassium or sodium hypophosphite as a byproduct. 3Co plus P4 plus 3H2O right pointing arrow 3KH2PO2 plus pH3. Alternatively, the acid-catalyzed disproportioning of white phosphorus yields phosphoric acid and phosphine. Both routes have industrial significance. The acid route is the preferred method if further reaction of the phosphine to substituted phosphines is needed. The acid route requires purification and pressurizing. It can also be made, as described above, by the hydrolysis of a metal phosphide, such as aluminium phosphide or calcium phosphide. Pure samples of phosphine, free from P2H4, may be prepared using the action of potassium hydroxide on phosphonium iodide, PH4I. It is prepared in the laboratory by disproportionation of phosphorus acid 4H3PO3 right pointing arrow pH3 plus 3H3PO4. Phosphine evolution occurs at around 200 degrees Celsius. Alternative methods involve the hydrolysis of aluminium phosphide, calcium phosphide, and tris trimethylsilyl phosphine. Phosphine is a constituent of the Earth's atmosphere at very low and highly variable concentrations. It may contribute significantly to the global phosphorus biochemical cycle. The most likely source is reduction of phosphate in decaying organic matter, possibly via partial reductions and disproportionations, since environmental systems do not have known reducing agents of sufficient strength to directly convert phosphate to phosphine. It is also found in Jupiter's turbulent atmosphere, where it forms in the planet's hot interior and reacts with other compounds in the upper atmosphere. The abiotic synthesis of phosphine takes enormous amounts of energy, such as in the planet-sized convective storms of gas giants. Phosphine has also been detected in the temperate zone of Venus's atmosphere, approximately 50 km altitude, at 20 ppb, a concentration which is not possible with known chemical processes. Venus lacks the high temperatures and pressures to form phosphine the way gas giants such as Jupiter do, thus another explanation for its presence is required. It is not expected that phosphine would persist in the Venusian atmosphere, since being subject to ultraviolet radiation, it would eventually be consumed by water and carbon dioxide, thus it would have to be replenished. The paper announcing the discovery suggests that the phosphine could originate from unknown photochemistry or geochemistry, or, by analogy with biological production of pH3 on Earth, from the presence of life. For this reason, phosphine has been proposed to be a usable biosignature for astrobiology. pH3 is associated with anaerobic ecosystems on Earth, which may be indicative of life on anoxic exoplanets. As of 2019, no known abiotic process generates phosphine gas on terrestrial planets in appreciable quantities, so detectable amounts of phosphine could indicate life. The Vega mission probe found rich reduction-oxidation chemistry between different phosphorus species and water at Venusian clouds, including phosphoric acid and phosphorus anhydride P4O6. Phosphorus anhydride P4O6 was found to be the major phosphorus species of clouds below 25 km. Phosphorus anhydride can react with water forming phosphorus acid, which at elevated temperature disproportionates into phosphoric acid and phosphine. Organophosphines are compounds with the formula PrNH3-N. These compounds are often classified according to the value of N. Primary phosphines N equals 1, secondary phosphines N equals 2, tertiary phosphines N equals 3. All adopt pyramidal structures. Their reactivity is also similar. They can be oxidized to the phosphorus V level. They can be protonated and alkylated at phosphorus to give phosphonium salts, and, for primary and secondary derivatives, they can be deprotonated by strong bases to give organophosphide derivatives. Primary phosphines are typically prepared by alkylation of phosphine. Simple alkyl derivatives such as methylphosphine CH3PH2 are prepared by alkylation of alkali metal derivatives MPH2, M as Li, Na, or K. Another synthetic route involves treatment of the corresponding chlorophosphines with hydride reagents. For example, reduction of dichlorophenylphosphine with lithium aluminium hydride affords phenylphosphine, PHPH2. Secondary phosphines are prepared analogously to the primary phosphines. They are also obtained by alkali metal reductive cleavage of triarylphosphines followed by hydrolysis of the resulting phosphide salt. The latter route is employed to prepare diphenylphosphine, PH2PH. Deorganophosphinic acids, R2-phosphorus monoxide O, can also be reduced with diisobutyl aluminium hydride. Secondary phosphines are typically protic in character. But when modified with suitable substituents, as in certain, rare diazophospholines, scheme 3, the polarity of the pH bond can be inverted, c. Umpolung, and the resulting phosphine hydride can reduce a carbonyl group as in the example of benzophenone in yet another way. Tertiary phosphines are generally obtained by treatment of phosphorus trichloride or triphenylphosphite with organolithium reagents or Grignard reagents. They are commonly used as ligands in coordination chemistry. Tertiary phosphines of the type PRAR are p-chiral and optically stable. Secondary and tertiary phosphines occur in cyclic forms. 3-membered rings are phosphiranes, unsaturated, phosphyrenes, 5-membered rings are phospholanes, unsaturated, phosphol, and 6-membered rings are phosphinanes. Phosphine is a precursor to many organophosphorus compounds. It reacts with formaldehyde in the presence of hydrogen chloride to give tetrakis hydroxymethyl phosphonium chloride, which is used in textiles. The hydrophosphonation of alkenes is versatile route to a variety of phosphines. For example, in the presence of basic catalysts pH3 adds of Michael acceptors such as acrylonitrile, pH3 plus 3 CH2 equals CHZ right pointing arrow P, CH2 CH2Z 3, Z as NO2, CN, or carbon monoxide NH2. Acid catalysis is applicable to hydrophosphonation with isobutylene and related analogues. pH3 plus R2C equals CH2 right pointing arrow R2, CH3, CpH2, R as Me, alkyl, etc. Phosphine is used as a dopant in the semiconductor industry, and a precursor for the deposition of compound semiconductors. Commercially significant products include gallium phosphide and indium phosphide. For farm use, pellets of aluminium phosphide, calcium phosphide, or zinc phosphide release phosphine upon contact with atmospheric water or rodent stomach acid. These pellets also contain agents to reduce the potential for ignition or explosion of the released phosphine. A more recent alternative is the use of phosphine gas itself, which requires dilution with either CO2 or N2 or even air to bring it below the flammability point. Use of the gas avoids the issues related with the solid residues left by metal phosphide and results in faster, more efficient control of the target pests. Because the previously popular fumigant methyl bromide has been phased out in some countries under the Montreal Protocol, phosphine is the only widely used, cost-effective, rapidly acting fumigant that does not leave residues on the stored product. Pests with high levels of resistance toward phosphine have become common in Asia, Australia and Brazil. High-level resistance is also likely to occur in other regions, but has not been as closely monitored. Genetic variants that contribute to high-level resistance to phosphine have been identified in the dihydrolipoamide dehydrogenase gene. Identification of this gene now allows rapid molecular identification of resistant insects. Phosphine gas is denser than air and hence may collect in low-lying areas. It can form explosive mixtures with air, and may also self-ignite. Phosphine can be absorbed into the body by inhalation. Direct contact with phosphine liquid, although unlikely to occur, may cause frostbite, like other cryogenic liquids. The main target organ of phosphine gas is the respiratory tract. According to the 2009 U.S. National Institute for Occupational Safety and Health (NIOSH) Pocket Guide, and U.S. Occupational Safety and Health Administration (OSHA) regulation, the 8-hour average respiratory exposure should not exceed 0.3 ppm. NIOSH recommends that the short-term respiratory exposure to phosphine gas should not exceed 1 ppm. The immediately dangerous to life or health level is 50 ppm. Overexposure to phosphine gas causes nausea, vomiting, abdominal pain, diarrhea, thirst, chest tightness, dyspnea, breathing difficulty, muscle pain, chills, stupor or syncope, and pulmonary edema. Phosphine has been reported to have the odor of decaying fish or garlic at concentrations below 0.3 ppm. The smell is normally restricted to laboratory areas or phosphine processing since the smell comes from the way the phosphine is extracted from the environment. However, it may occur elsewhere, such as in industrial waste landfills. Exposure to higher concentrations may cause olfactory fatigue. Deaths have resulted from accidental exposure to fumigation materials containing aluminum phosphide or phosphine. It can be absorbed either by inhalation or transdermally. As a respiratory poison, it affects the transport of oxygen or interferes with the utilization of oxygen by various cells in the body. Exposure results in pulmonary edema, the lungs fill with fluid. Phosphine gas is heavier than air so stays nearer the floor. Phosphine appears to be mainly a redox toxin, causing cell damage by inducing oxidative stress and mitochondrial dysfunction. Resistance in insects is caused by a mutation in a mitochondrial metabolic gene.